Today we're going to learn about buffers. I don't know if you recognize that, but that's a drawing of a blood vessel. We have buffers in our blood, and there's actually buffers in the environment. They're used in industry, so it's an extremely important concept in chemistry. So what is a buffer? A buffer is a solution that resists changes in pH when either a strong acid or a strong base is added. Now, what composes a buffer? A buffer has two components, a weak acid and its conjugate base. So those are the two parts of a buffer. Now, how does a buffer work? So to do that, we might want to compare two solutions, a non-buffered solution and a buffered solution. So if you take a liter of water and you add 0.01 moles of HCl to it, so we're adding 0.01 moles of HCl to a liter of water, the pH changes drastically. It goes from a neutral pH of 7 to a pH of 2. However, if we take a buffered solution of the same volume that's buffered with, for example, it could be a buffer with acetic acid and sodium acetate, there's only a slight change in pH. Now you notice in the drawing I have here, the pH of the solution is 7. Buffers could actually be, or solutions in our buffers could be at a pH of 7 or any pH. But the point is, whatever pH that buffer is set at, when you add acid or base, the pH doesn't change very much. So how do you make a buffer? So how are buffers prepared? Well, remember the goal of the buffer is to have a weak acid and its conjugate base. So hopefully you remember the difference between a weak acid and a strong acid, because that's going to be real important in this discussion. So you see here we have a weak acid, that's acetic acid, and we have its conjugate base, which is the acetate ion. Now you wonder, what in the world is the sodium doing there? The reason the sodium's there is because sodium acetate is actually how you would get the acetate ion. So we know that we're going to actually use acetic acid, but we're going to actually also have to use a compound such as sodium acetate. Because what happens when you put, which is a salt of the weak acid, so what happens when you put sodium acetate in water? It dissolves and gives you two ions, because family 1A, of which sodium is a part, is completely soluble. So when that dissolves, you get sodium ions and acetate ions. Now, we don't care about those sodium ions, so we're going to cancel those out, just cross those out. Those are what we call spectator ions, but the acetate ions are extremely important because that's the second part of our buffer. So to make a buffer, we'd really use two things. We'd use acetic acid, and we would also put in that solution solid sodium acetate, which would dissolve and give us acetate ions, and thus we'd have a buffer. And here we're ready to go. How do buffers work? What makes them resist changes in pH? For that, we're going to do one of my favorite things, which is to write balanced reactions. So first, let's say we have the weak acid portion of the buffer. What it does is the weak acid absorbs the base. Now, hopefully you remember a base is actually hydroxide because we're adding a strong base. So you have acetic acid plus a hydroxide, and when that reacts, notice it's a completion arrow because we've added a strong base, and so this reacts completely. That hydroxide, as long as there's enough acetic acid, is turned completely into water, and the acetic acid is turned into acetate ions. Notice at the end there's no hydroxide, so this has prevented our solution from becoming basic. So what absorbs the acid part? Well, that's where the conjugate base comes in handy. The conjugate base absorbs any added acid. So that reaction will look like this. We'd have an acetate ion plus a proton, and together they would form acetic acid. Notice at the end there's no more protons left, so we're going to cross those protons out. And now we've gotten rid of the protons, so we no longer have an acidic solution. We have acetic acid, which we know that's a weak acid, and it only produces a few protons, so there's not really much of a decrease in pH when you produce acetic acid. So why all this discussion about buffers? Well, we said they're super important. For example, here I have goldfish. Goldfish can only survive in a certain pH range, much the same as cells of any living system. Goldfish usually can survive if it's between a pH of 6.5 all the way up to 8.25. But you get out of that pH range and the goldfish unfortunately will die. So let's look at a pH or a buffer that is important to the human body. Like we said, buffers are important to biological systems. We're going to talk about humans here, for example. So the cells of living organisms can only survive in a narrow pH range, and buffers allow that to happen or keep the pH within that narrow range. For example, humans have a bicarbonate buffer in their blood, and that means it maintains a pH between 7.35 and 7.45, which is an extremely narrow range. You notice here we have the bicarbonate buffer. Here we have carbonic acid, H2CO3, and here we have bicarbonate, or the conjugate base of that weak acid. So those two things together make the buffer in human blood. So we could say it's a bicarbonate buffer. Buffers are extremely important to crops. For example, crops can only grow within certain pH ranges. The soil can either be too acidic, and if it's too acidic, that can affect plant growth and increase the deposit of toxic minerals, which you don't want. Or soil can be too alkaline. Alkaline is another word for too basic when it's much above 7, and that's not good for plant production either. You don't have to write down any of these numbers, but I just wanted you to see this as an example. Different plants and that have an optimal pH range. So if a farmer was, for example, growing alfalfa, he would want his crops or his soil to be within a range of 6.6 to 7.0. Or something we see here in the Midwest, corn is a very important crop. So corn, we'd want a pH between 5.8 and 6.2. And so the farmer would add different chemicals to the soil to maintain this specific pH range so it would have the optimal growth conditions for the plant. Now, something else we see here is acidic versus alkaline. This alkaline may be a new word for you. I think we all know what acidic is. Alkaline, once again, just means it's too basic. Now, you see here in the middle, these are minerals that we want deposited from the plants. And that's when it's within that healthy range. But notice if we get outside that range, these other minerals are deposited, which are not healthy. For example, if the soil is too acidic, there could be a high concentration of aluminum ions or manganese ions, and that's something that can be, those are toxic materials that we don't want to accumulate, for example, in corn or other materials that are being grown. This is actually a pH test kit that a farmer would use to test the soil to make sure the pH is in a certain range. Much the same as the pH kits we used in the lab when we did the lab with different substances to test to see if there are acids or bases. This is actually the production of metal. Metals are plated, and in doing that, one thing that they do is they want to maintain with the solutions in which the metals are plated in a process they call electroplating within a certain pH range. And this is important for the production of alloys, which is a huge chemical production material throughout the United States. Next, also leather. Leathers, when they're prepared, need to be within a certain pH range. The manufacturing of leather is yet another place where pH. Also, Jell-O, yet another place. And we think of gelatin being used in Jell-O. Gelatin is actually used in a vast array of materials, be they pharmaceuticals or food or other materials. But gelatin is another place. When that's manufactured, it must be in a certain pH range. And lastly here, I have pharmaceuticals, because pharmaceuticals as well need to be within a certain range when they're manufactured, because when they're in the human body, we want them to be able to react appropriately, and the pH range is very important for pharmaceuticals and drugs. Which of the following combinations would act as a buffered solution? So this is one of the things you should want to be able to recognize. So let's go through each of these examples. Would HCl and NaCl, would that be a buffered solution? Hopefully you said no. The reason that would not be is because HCl is a strong acid, and to be a buffered solution, you need a weak acid. So that is certainly not a buffered solution. So once again, you need to remember your list of strong acids, and remember all the other acids are weak. The next choice is acetic acid and potassium acetate. Would that work as a buffer? The answer is absolutely. Acetic acid is a weak acid, and potassium acetate is a salt of that, and when the potassium acetate dissolves, it will produce the acetate ion, which we see here, and so you'd have the conjugate base of the weak acid and the weak acid, and then you'd definitely have a buffer, so that's definitely a buffer solution. Next choice. Dihydrogen sulfide and sodium hydrogen sulfide, would that be a buffer? The answer is absolutely, because when sodium hydrogen sulfide dissolves, you get hydrogen sulfide ion, which is a conjugate base of, what is the name of that acid, H2S? The name of that acid is hydrosulfuric acid. Remember, this acid does not contain the element oxygen, and if it doesn't contain the element oxygen, we add the prefix hydro. So this is hydrosulfuric acid and hydrogen sulfide, and so that is definitely a buffer. Last question. Hydrosulfuric acid and sodium sulfide, is that a buffer? The answer is no. It would only be a buffer if it's lost one proton. That compound is without two protons, so that is not the correct conjugate base of that buffer. So it lost two protons. Next question. Show how the following buffer works. And we're going to look at a couple examples here. The first one, we're going to look at basically the ones that we said were buffers. We've got acetic acid and potassium acetate. Now, hopefully you remember this. We actually looked at this reaction earlier. Yes, we said this was a buffer, and so what would happen, the acetic acid would react with the hydroxide, which is our strong base, to produce water, and acetate ion. And so when it does that, that removes all the hydroxide, and so it buffers or removes the hydroxide from the solution. And how is the acid removed? Well, the acetate ion reacts with a proton, produce acetic acid. That removes the proton from the solution, and so that is how it buffers it and keeps the pH from going low. Let's look at the other one that we said was a buffer. Remember, we also said that hydrosulfuric acid was a buffer with sodium hydrogen sulfide. How would that work? So what would happen is a hydrosulfuric acid would react with hydroxide, and when it did, it would produce water and a hydrogen sulfide ion. And in doing so, it will remove the hydroxide from the solution. Hydroxide is removed, and it's buffered the base, or kept it from being alkaline. How would the sulfide or the hydrogen sulfide ion work? It would react with the protons, and in doing so, it would remove those from the solution, so there's no more protons, and produce hydrosulfuric acid. So in doing so, this is buffer the solution, removing both proton and hydroxide, strong base and strong acid, from the solution. I love chemistry. Chemistry. I love chemistry. I love chemistry.